A 4-mile ride costs $107.
If you look at any complex system, a flock of birds, a shifting stock market, the weather, you see a massive, tangled web of moving parts. Without a way to track the individual pieces, it is just a chaotic blur of action. Isolating the specific starting condition that triggered a result turns raw observation into usable data. We have to identify the cause and its effect. This is exactly why mathematicians use function notation. It is a standardized tracking system designed specifically to lock those relationships into a readable format. Our goal is straightforward. Take a single, specific starting value, an input, and follow it through a mathematical rule to confirm its exact matching output. Function notation prevents data chaos by taking an invisible chain reaction and transforming it into a precise, trackable record. Let's start with the first step in this causality chain, testing a direct mathematical rule to observe its effect. Consider the function c of t equals 18t plus 35. In this case, the rule calculates the cost of a ride after t miles. To find the cost of a 4-mile trip, we substitute the input 4 for the variable t in our function rule. Now we compute. 18 times 4 is 72. We add 35 to 72, bringing us to 107. C of 4 equals 107, so the ride costs $107 after 4 miles. By evaluating the rule, we definitively linked our isolated starting condition, the distance, to its physical outcome. Sometimes the math is already calculated for us. When that happens, our job shifts from executing arithmetic to translating the resulting notation into plain language. Look at the function h of d. This represents the height of a plant in centimeters after d days. If we analyze the specific notation h of 12, the input 12 stands for 12 days. The function output represents the plant's height for that exact day. So h of 12 means the plant's height after 12 days. This notation provides a complete descriptive sentence about a physical event.
H of 12 means the plant height after 12 days.
Mathematical rules are bound by the real-world constraints they describe. We can test this by analyzing what happens when data falls outside the expected range. Imagine a school that sells tickets numbered strictly 1 through 300. We have a function, s of n, that gives the assigned seat row for ticket number n. Does the statement s of 412 represent a meaningful value in this specific context? The ticket numbers in the situation go only from 1 to 300. The input 412 is mathematically possible as a number, but physically outside the valid domain of the scenario. No, s of 412 is not meaningful because 412 is outside the domain. The domain enforces the boundaries. It dictates the hard physical limits of where a mathematical cause and effect relationship actually exists. We don't always use active equations. When processes are already completed, we transition to extracting data directly from an archive. This table for function p displays the known records. P of 0 equals 4, P of 1 equals 7, and P of 2 equals 10. To find a specific result, we scan the archive to locate the row where the input is 2. From there, we trace the path directly to its corresponding output in that pair, which is 10. P of 2 equals 10, the output paired with input 2. Tables serve as a static map of causality. We read the notation by simply locating the matching pair. Whether evaluating a rule, checking a domain, or reading a table, the goal remains the same: using function notation to record a mathematical event. In just a few characters, it displays the starting trigger, identifies the specific system being used, and confirms the consequence. Mastering functions requires you to match the specific quantities in a given context to their exact symbolic notation. Mastering these relationships depends on finding the evidence in the environment that definitively links a starting action to its final outcome.
Ticket 412 lies outside 1 through 300.